Okay, hello everyone, welcome. Can you hear me? Hello.
Yes,
Okay, just for
the
waiting 1 minute, then we start. Okay, let's go start at this session. So hope all are well and already get all of previous material. Okay. So basically today is our fourth number days. Okay, so let me share my screen. And after completing the live 3 hours live training, then we talk about the problem solving class. Yeah. Okay, let me share my screen. Can you see my screen?
yes.
Okay, thanks. So let's go start. Okay, so basically today I discussed about that how to remove cloud and haze from the satellite imagery, then how to work with DEM data, basically digital elevation model, and how we can easily create different types of topographical mapping such as hillshade map, slope map, or aspect map. How we can easily create, we'll also discuss about that. Then we'll talk about the LST monitoring, land surface temperature, using Landsat satellite data, how we can easily monitor or estimate land surface temperature, use Landsat satellite data. Okay. And then how to calculate average, maximum, minimum NDVI for any specific region. After LST, we also talk about the urban heat island, how we can easily identify. Then how we can easily identify the effect of urban heat island. Where is the high effect? Where is the low effect? So this type of things we'll also discuss about that. It's called the urban thermal field variance index, and also discuss about the time series chart. Okay. And previous class 2 topic is not complete for the monthly time series and also annual time series, how we can easily create. So this thing I also try to explain in this session also. Then you can easily get the idea how it work. Okay. So first of all, we discuss about that LST, land surface temperature. So we already use the Modis LST. Okay. So Modis is one kind of ready-made product. We can easily use the Modis and make the LST. But Modis resolution is not good. We find out that it's 1000 meter. Pixel size is 1000 meter. So when you use the Modis in the small study area, then it's not show the better result. Okay, we find out that grid or cell, because this cell size is very big or high and resolution is 1000 meter. Okay, but when you work with a small study area, it's better we try to use the Landsat satellite data, mainly Landsat satellite imagery, and make the LST. But Landsat satellite data, it's not provide you the ready-made product like as Modis easily provide the ready-made product and we can easily use without any kinds of analysis. But when you are using the Landsat satellite data, you must need to make a algorithm, and now just you make a analysis. Okay, mainly satellite image analysis, and drive the LST information from this satellite imagery, because it's not the ready-made product. So for that we need to read some scientific paper okay, because already a lot of work is already done to use the LST. So you can also follow this type of method, or then also apply in the Google Earth Engine and make the analysis. So if you simply check some paper, so please simply go to the Google Scholar and simply search different types of paper. We also find out in the Google Scholar, and then we just use it, this type of paper. Okay, suppose if I show you some paper. So this is the one kind of paper assessing and predicting land use, land cover, and land surface temperature. So in this paper, it also used the land surface temperature. Okay, and this is another paper modeling the impact of the land use, land cover changing pattern on the urban thermal field variance index. This type of paper, it also used the Landsat imagery and then make the LST. Okay, and not only for that, lot of paper is already published. They are already worked LST, and this LST we can easily connect with different types of parameter. Suppose in this paper, it connect with the land use, land cover, and also urban heat island, and also urban thermal field variance index. Okay, for Dhaka metropolitan area. And this is the same work. So this is another one. So it also work with same land use, land cover changing pattern on urban thermal field variance index. Okay, so LST is very important element. Okay, in the remote sensing, we can easily connect different types of land use, land cover, or also urbanite island. Okay, so we can easily connect this LST. So if you check this type of paper, so it also use some method. So you can also follow this type of method, or if you want, you can also search other method. We find out a lot of method, this type of things you can easily find out. So I was in, if you check this paper, okay, let me show you that. So in this paper, they are used at the land surface temperature LST using satellite imagery. Okay, Landsat satellite imagery. Okay, just a minute. I think let me share the one tab. Yeah. Yes. So in this paper, basically it used the Landsat satellite imagery for the different time period. Okay. So you can see that used the Landsat 5, Landsat 8, because it's the make the historical data analysis also, and also further also prediction work. Okay. And further identify urban thermal variance index to identify. So let's go. In this case, we will just talk only for the LST. Okay, LST, and talk about the urban heat island, and also talk about the urban thermal field variance index. So this type of index, how we can easily compute, we also discuss about that. Okay, for today's session. So you can see this is the formula about that urban heat island. This is the formula for urban thermal field variance index. Okay, and further it also work for the future prediction also. So use the artificial neural network, okay, CA algorithm, and further it also predict the land use, land cover for the future. Okay, so let's go how we can easily create this type of LST and urban island. We'll also discuss about that. Not only for that, if you simply search on the Google, so you find out the lot of paper, okay, regarding this type of LST. Suppose I simply search LST monitoring using Landsat 8, so we can easily find out lot of paper is already published regarding using the Landsat satellite data. So you can see this is another paper. So in this time, this is the follow chart about this work. So they are take the Landsat data, further they are compute the take the three band, mainly thermal infrared band, and then near infrared band and red band. So then use the near infrared band and red band to make the NDVI. After NDVI, compute the vegetation proportion, then compute the surface emissivity. Then from the thermal infrared band, they calculate the brightness temperature. Okay, and further just apply the mono window algorithm and then compute the LST, okay, or land surface temperature for this study area. Or if you want, you can simply search here, suppose LST, okay, LST, simply search LST or land surface temperature, just use this keyword. So then we find out the lot of paper. Suppose land surface temperature. So you can easily find out, you can see this type of paper: satellite graph land surface temperature, current status and the perspectives, land surface temperature, satellite remote sensing, global land surface temperature, estimating land surface evaporation. Okay, so different types of topic you can see: land surface temperature. Further, you can see this is the identify relationship between land use, land cover change, and land surface temperature. Okay, so you will try to read this type of paper. Okay, then you can get the more better idea. And further, we just try to apply this type of method or algorithm in Google Earth Engine. Okay, so let's go try to follow one paper, and then step by step we try to compute. So in this case, we are using the Landsat satellite imagery. And when you are using the Landsat satellite imagery, then we need the 3 band. Okay, first band, basically we need near infrared band, red band, and also brightness temperature or thermal band we need. Okay, and then we just apply this type of algorithm, and we can easily compute the LST using the Landsat satellite imagery. Okay, so let me open a code editor. So first of all, we need to import a satellite imagery. So in this case, we are just using the Landsat. Just I call the satellite imagery Landsat. Okay, I use here this was Landsat 8. And in the Landsat 8, we are just work with the surface reflectance. Okay, surface reflectance. When you make the land surface temperature or land use, land cover, try to use the surface reflectance. It will be more better. Reflectance will you find out. But when you work with the different types of indices, then try to use the top of atmosphere reflectance. But when you work with the land use, land cover, or land surface temperature, then surface reflectance is more better. So this is the surface reflectance satellite imagery for Landsat 8. And if you check here, we find out all of band. Basically, SRB1 is the coastal aerosol or a ultra blue band. Then SRB2, it's a blue band. SRB3, it's a green band. SRB4, red band. SRB5, okay, it's a near infrared band. Then SRB6, short wave infrared 1, and SRB7, short wave infrared 2. So this type of band, as well as if you check, this is a thermal band, STB10. So this is a thermal band. Thermal band basically brightness temperature or surface temperature. This is a thermal band, and this unit is the Kelvin. Okay, this unit is the Kelvin. So further, we can simply convert into degree Celsius. So I'll just show you this process also, how we can easily convert. So this image collection, just import in your code editor. Just copy the snippet ID and then paste in this code editor. And you can set any name. So I set the name, suppose L8 and equal. So now this is the image collection. This image collection is stored in this variable. Yeah, any question, please?
Quick question.
Please.
Landsat and Sentinel-2 seems to have higher resolution than Landsat, but why do you prefer normally working with Landsat on your example?
Sentinel-2 satellite imagery. Okay, so it's defined on the bands. Suppose all near infrared band or thermal band is not available for the Sentinel-2. Okay. Okay, suppose this type of thermal band, if you check, this band STB, this band, it's called the thermal band. This band is only available for Landsat. Okay, that's the reason we are just using the Landsat image to make the compute the LST. We are not using the Sentinel-2. Okay, but Sentinel-2 is more better resolution than Landsat, but there is no band about thermal band. Okay, thermal band is only available for the Landsat satellite data. Okay.
Okay.
So now we just simply import this image collection and further simply filter your study area. So let's go and try to work. Just import a shape file. Suppose that's just we import a study area. So just let me import the study area of Dhaka city boundary. And then give a variable name. We can put any name. Suppose I put the name is RY. So now same process, we already know, lot of time we are just filtering process. We already know how we can easily filter the Landsat image collection or Sentinel image collection. Just simply filter. So take a variable, I put the variable name, suppose image, and call the L8 and put here the filter bounds function. So it intersecting all of collection for all my study area is ROI. Okay, and then put here dot filter suppose filter date. Suppose I want to observe the LST in year of 2024. So put here the time, suppose 2024 1st January, and put the time, suppose 2024 December 31. Okay, so now put the dot filter metadata. Okay, so this is the function. So now this function, if you want, you can also use it, there is no problem, but better to use where you add this function. It's called the filter. And how I can filter? Earth engine dot filter, then less than. So now just put the keyword and key value, mainly what less than what, it's just put the value. It's a cloud cover, less than 1. So now if you check how many images we find out for that, just use the size function and run the code. We found the 4 images. Okay, or if you want, you can also use the filter metadata. Also there is no problem. Okay, suppose for filter data, how I can represent, just put the filter metadata, then put the property name, it's a cloud cover, then operator less than, and set the value, suppose 1. So we find out the same number of images just on the 4. Okay, so this is the two way we can represent the filtering image properties, but same work. So in this case, this last one is more better. Okay, so now I simply find out the 4 images. So now 4 images, you want to check all of information about the 4 images. Suppose just put the print and image, and you can also find out the single image information. Suppose you want to work with the single date imagery, just copy the feature and copy the image ID. Okay, just copy the image ID and then work with the single date imagery. So this is the process, because some if you check some paper, they are use the single date imagery for LST. Suppose this image acquisition time, if you check from the properties, this is the image, you can see 9th March 2024. Okay, suppose this time I just simply take this image for this day and then make the LST. So it is also possible. So for that, simply copy this ID, and this ID store it in a variable, and further apply the same work. Okay, so when you work with a single date for estimating LST, just apply this process. Or if you want, you can just make the composite. So let's go, I try to work with the composite. So just I put here the dot median. So now it's create the composite, and this composite I just clip with my study area. So put here the dot clip, shape file is the ROI. Okay, so now I create the composite, but it is also possible. You can also take the single date imagery and then also work, no problem. So when I composite median, and if I just print this image, so now it work as the image. If you check, it show the image computing, because now it's just create a composite median composite single image, and this single image have total 19 bands. So you can see all of bands we have. Okay, so we find out this type of things, and further if you want, you can also just add the layer of this image. So map.add layer and call the image, and also focus on your given study area. So map.center object.
One question.
Please.
The filter bounds based on ROI. I thought it does almost the same job as the clip.
No.
It will give you only within that specific boundary, no?
Filter bounds, basically it intersection. Suppose I have a boundary. Suppose this is my study area. If I the practical, suppose this is my geometry. Suppose this is my area of interest. So in this area of interest, how much satellite tiles intersect? Suppose one tile just come from here, another tile just come from here, another tile just come here. So filter bounds function, it just identify only for those how many images intersect in your study area. But when I use the clip function, suppose I have an image, so but this image I need only for this boundary. So just I use the clip, so then it cropping only for my study area of this image. Okay, but filter bounds, it intersect in your study area, how many images are available, intersect mainly just overlay. Suppose one tile just come in here, another tile just come in here, another tile just come in here. So just it's identify, intersect in your boundary how much images or how much tiles, and then clip just cropping with your image, final image.
Thanks.
Okay. Okay, so we find out that and just I put suppose 10 zoom level and run the code. So I display the image. We find out this type of imagery, and if you check, suppose I want to add the color, so red, green, and blue. Okay, and instance I keep the 98%, and you can see it show very large. It's a digital number. Okay, it show the digital number, and if I just apply it, it's not mandatory, because in this time if you want you can also convert the reflectance value also, then it will be more better. For the converting the reflectance value, just simply use the offset value and also use the scale value. You can see it show the scale value and offset value. Okay, then you can simply just find out the more reflectance value. Okay, but in this time I don't need for all of bands. Okay, because I just need only for the 3 band. Okay, basically I need the near infrared band, red band, and also this STP10. Okay, and STP10 is very important thermal band, because I just use this reflectance value and estimate the surface temperature. So when I use this band, then I also use the scale value and also offset value. Okay, so now it's not need, it's optional. If you want you can also add the offset value or scale value and then work, so no problem. But when you work with the land use land cover to get the proper wavelength value or reflectance value, then we just make the rescaling. Okay, or convert digital number into reflectance value. Okay, otherwise it's not need, just a import the same or default, because we are not use this because from the image we just take only for the 3 bands. Okay, we don't need the whole image, it's not need all of bands, we don't need. I paste here and put here, suppose it's a image. So now we find out the image, this type of image. Suppose I want to use this image and okay, just a minute, why it not showing the color? Just expressing again, and I put here suppose red, then green and blue. Apply and then import. So now remove the previous ones, it's not need, and copy the new one, just copy and paste after the object and run the code.
One more question, sir.
Please.
What if, assuming my interest is to export single bands, for example, filter and get only the infrared alone and the red alone for me to be able to process in ArcGIS?
Yes, it is also possible. So
you
for
do
that,
the filtering from this part or from which part?
So for that, simply use the select function and then select your single band. Suppose you need the SRB5 and then further export this image. Okay, so then we find out only for the export only for the SRB5 bands. Okay, suppose you need the red band, so SRB4, just simply select the single band. Okay, so when you export, suppose I want to export only for the SRB4, so just I use the select function and put my band name. So now this image is only stored at this band. If you check, if I run the code, what happened, you can check. So it just stored only for the single band. You can see the band is 1. Okay, this image band is 1, SRB4. So when I export this image, what happened, it just export only for the 1 band. Okay, suppose you need the multiple band export, just put suppose another one. Suppose I just need SRB3 and run the code. So now when I export this image, it exported 2 band, SRB4 and SRB3. You can see this image. When I print this image, it show the result. There are the 2 bands, and I make a mistake in here because you can see I just use the print function and then I apply this visualization parameter or others. So that's why it not work. So print function just we print only for the image variable, and this type of thing we simply connect with the map.addLayer function. Okay, and I put the it's a layer name image. So now run the code. So now we find out that proper visualization, but it show that SRB2. Why it show the problem? Because I just select the SRB4 and SRB3. Okay, just I fixed the two band, but this visualization parameter it added, you can say SRB3, SRB4, SRB3 and SRB2. So that is the problem. It show a problem. You can see it show that bands name SRB4 and SRB3, but SRB2 there is no SRB2. Okay, so when I just simply put here suppose SRB2, then in this visualization parameter all of bands I just simply choose and select in my image. So now I hope it will work. There is no problem. Okay, there are the three bands. Okay, and this three band I just make the combination in here, SRB red, green and blue. There is no problem. And if I not select any band, then what happened? It's including all of bands. Just run the code. So it's including total 19 bands. Suppose I want to work only for the single band, I want to export only for the single band, just select. Suppose I select only for the SRB4, and it show a problem because I already add this visualization parameter. You can see if you check this variable stored SRB4, SRB3 and SRB2. It just create the combination and then store it in the visual parameter in here. But if you want, you can simply put the empty and run the code. So now it will work. There is no problem. So now it display only for the single band SRB4 band. It display in this map. Okay, SRB4 band. Suppose I want to display SRB5. So now run the code. So now it display only for the SRB5 or near infrared band. Okay, and it look like that. I want to display suppose SRB5 and I want to identify where is the high reflectance, where is the low reflectance, just stress in 98%. And I just if you want, you can also add the color. So I put the grayscale color. Just run. You can see this type of white color indicating about the high reflectance value. Okay, this type of white color is indicating about the high reflectance of near infrared band. Okay, and this type of black color indicating about the low reflectance of SRB5 or near infrared band. Okay, and when you export, suppose when you export this image, then it export only for the SRB5 band. So when you export, just try to use the select function and select for a specific band which you need, and then just work and easily export a specific single band. Okay, so now we find out this type of image, and this image I just use, and further I just make the LST. So when you make the LST, first step we need to make the NDVI. So first step, compute NDVI. So NDVI formula we already know, near infrared minus red divided by near infrared plus red. So this is the formula. Okay, and this formula you can compute different way. Okay, different method. Previous class I discussed how we can easily compute different types of indices. Okay, so let's go try to compute this near and then check what happened. So take a variable, suppose NDVI. Okay, and call the image. From this image, just apply the normalized difference between two band, near infrared band and red band. Okay, so now it's compute the NDVI. So let's go try to just add the layer. So map.addLayer and call the NDVI and run the code. So now it also added the NDVI map. From this image we find out that it show this type of grayscale. If you want, you can also add the color to look more better. Just click on this and add the different types of color. So just I stressing suppose 98%, and I want to add the color. Suppose low value or negative value, it show this type of blue color. Then get at, then I need to choose suppose this type of white color, or you can put any color. And then I put suppose green color. Okay, and then just apply. So now green color indicating about the vegetation area. So this type of is not non-vegetation area. So we can easily identify this type of green color is the vegetation. Okay, so now import this visualization parameter. Just copy and paste after the object name. So this is the object, and after the object always we put visualization parameter, then put layer name. I put the layer name, suppose NDVI. So now it's compute the NDVI and also add the NDVI. So after computing the NDVI, second step, we need to compute proportion of vegetation. So this is second step. It's called compute PV, proportion of vegetation, or it's also called fraction vegetation, FV. So how I can compute? So if you check the different types of paper, so in this paper, let me show you that this paper. So this is the formula about the NDVI, and then if you check where is the yes, so you can see this is the formula about that. So PV represent the vegetation proportion obtained according to this is the citation also, and you can see this is the formula. So this formula basically NDVI minus NDVI minimum value divided by NDVI maximum value minus NDVI minimum value and then power 2. So when you compute this equation, then we find out the proportion of vegetation, okay, or fraction of vegetation. So let's go. So we try to compute this formula. So in this formula, we need the two value. First value is the maximum NDVI value and minimum NDVI value for my study area. Okay, minimum NDVI value and maximum NDVI value we need to compute. And then I can easily apply this formula. So let's go try to discuss how we can easily compute the minimum and maximum NDVI value for the Dhaka city. Suppose in the Dhaka city boundary, we need to identify maximum NDVI and minimum NDVI value. So take a variable, suppose max, and I need to compute the maximum minimum NDVI value. So this NDVI map is stored in a variable. So this variable is the NDVI, just I call the NDVI. So from this NDVI, I want to compute maximum value of NDVI. So when you compute any statistical for a specific boundary, suppose minimum value, maximum value, then total value. So when you compute any statistical value from a specific boundary, always we use a function. It's called the reduce region. Okay, reduce region. So this is the reduce region function. Reduce region. Okay, this is the function. So this function, when you work with a specific boundary, a specific region, to compute different types of statistical value, just use the reduce region function. So I want to use this function. Just copy. So I want to compute it from NDVI. Just connect reduced region and put all of those. So just make a dictionary, curly bracket start and curly bracket end. So now put the keyword and key value. Suppose reducer, I want to compute maximum value. So put here EE dot reducer dot max. Then geometry, it's your shapefile variable name, which is ROI. Scale is the resolution of the satellite imagery, 30 meter for Landsat, and others not need, just remove. It's optional. Okay. So now let's check what happened. When I just print the maximum. So print max and run the code. So now we can see it show the dictionary computing, and we find out the one property. It show the ND 0.4. Okay, so this is the maximum value of NDVI for this study area. So ND 0.4, but it shows as a dictionary. Okay, dictionary basically keyword and key value. But from this dictionary, I just need only for the value. So for that, you can simply apply dot values function. So when I put the dot values function, then check what happened. It just work as a list. Okay, in this list, I just get only for the values. But from these values, I need only for the I need only this value, not need the serial number. So it's a serial number. So from this serial number, I just need only this value. okay, not need the serial number. So for that, just apply the dot get function, get the serial number. So serial number 0. So when I put the 0, so now this 0 stored this number. Okay, so just run the code and check what happened. It show the result as a computed object. So now we find out only for this value, okay, without list, without dictionary. So this, if you run the code, it show the result as a computed object, but these things I want to work as a number. Okay, so these things I need to convert as a number, so then I can easily apply this number in any other equation. Okay, so how I can convert the number? So for converting number, just put a function ee dot number, start the bracket and also close the bracket. So now when I run the code, it display the number computing. So now this value is stored as a number in this variable max. So further, when I just use the max any other equation, so then it work as a number. Okay, the same process just apply for the computing the minimum. Just I copy the minimum, copy the same line of code and put any, I put the variable name suppose min, and I want to compute minimum value. Okay, and I want to print the min and run the code. So now it display the minimum value of NDVI. We find out this is the minimum value of NDVI. Okay, if you want, you can also put some note. Suppose I put the note, it's a NDVI mean. Okay, NDVI mean, it's optional. If you want, you can also ignore this part. And this is the result for NDVI maximum, NDVI max. And if you run the code, it did show the result. If you check, we also find out this type of note. So NDVI maximum value 0.4 and NDVI minimum value negative 0.1. Okay, so now we compute the maximum and minimum. And finally, if you check the equation, suppose PV equal, this equation is NDVI minus minimum value of NDVI. So NDVI minus minimum value of NDVI divided by maximum value of NDVI minus minimum value of NDVI. Okay, so this is the formula, and then whole equation we need to apply power 2. Okay, power 2. So this is the equation. So now we just compute the equation and compute the proportion of vegetation. So take a variable, I put the variable name suppose PV, and then call the NDVI. So we already compute NDVI. You can see this is the NDVI. This is the NDVI map. So NDVI dot, I put it suppose subtract. I put the direct equation subtract, then put the minimum value, then divide maximum value and subtract from minimum value. Okay, so now if you just check the result, and finally power 2 full equation, just start the bracket and close the bracket. Just I cover the full equation and put the POW and put the power 2. Okay, but when I this is the number. Okay, so when you store it or construct any new number, we just put here ee dot number because it's a server function and then power 2. So it's more better. It also work without this function, but when you work with the Google Earth Engine, try to always use the server function, because we already know about that. When you work with any new number, when you define any new number in the Google Earth Engine server, you need to apply the ee dot number function, and this is the 2. 2 is a number. Okay, so now just run the code and add the layer, suppose PV, and run the code. So now it's also added the proportion of vegetation. Okay, so we find out this type of layer. If you want, you can also add the color, but it's optional. Okay, so now after compute then PV, then we talk about that how we can easily compute the, it's a, I think third step. Yeah, third step compute emissivity, EM. So this emissivity formula is proportion of vegetation multiply with the two constant value 0.004 and plus 0.986. So this is the proportion of vegetation, and multiply with 0.004 and 0.986. When you add, then we find out the EM. So a lot of paper also use some different value. So basically it also depend on the natural condition. So this type of value, it also depend on the natural condition or urban condition. Okay, it will be changed. So if you check, suppose I show the one paper, just a minute. Where is the paper? So you can see it's this paper. So basically emissivity value. Okay, so they are put this type of things, they are not compute. So based on the NDVI, we can set the emissivity value also. Okay, so you can see emissivity value with their corresponding NDVI values. So if the NDVI values less than negative 0.185, then we just use this type of value for emissivity or spectral emissivity. And if the range between this range 0.970, okay, and also you can see if the range 0.1572 to this value, then we find out this type of value. Okay, and if the NDVI value greater than 0.7, then we are just use the emissivity value. This is the emissivity value. Okay, and it's provide, if you can check the paper, then you can get all of citation. You can see, okay, NDVI is closely linked to the surface emissivity, hence the emissivity can be determined using the NDVI. Okay, table 4 illustrate the land surface emissivity value to indication there in respecting NDVI values. So we can also get the information from here also. Okay, and just use the emissivity value, okay, without calculation. Some paper also use this type of formula. If you check, this is the formula: proportion of vegetation multiply with the 0.04 and 0.986, then we compute the emissive value. It also possible to compute. Okay, so we try to use the formula and then compute, and then we try to compare on our NDVI mixed range, okay, with this paper. So what types of value we find out for the emissivity or EM. So for that, we already compute the PV, okay, proportion of vegetation. This one is already done. So now 0.04 and 0.986, these two number we need to just create. So take a variable. Suppose I take a variable, suppose A, and then EE dot number, and store the one constant value in this variable. Okay, for the variable name is, I put the variable, suppose A is the 0.004, and take the another variable, suppose B, and use their EE dot number and define the another value 0.986. So now we are applying this formula to take a variable, suppose EM, and then call the PV. I already compute the PV. This PV multiply with A, because A is stored at 0.004, and then add with B. Okay, so now add the map.add layer and use add the EM and run that. So now it's add the emissivity layer. We can see we find out this type of white color. So we try to put here stressing, and you can see it show the default name as a ND. Okay, because every equation when you compute, suppose this type of equation or any equation, this type of equation, if you don't use the rename function, then it show the default name as a ND. So you can see that's the reason it show the ND. But if you want, you can also change it. Suppose if I just put here the dot rename function and put name, suppose EM. Okay, so now it shows as a EM. Okay, but default any equation when you compute, if you don't change the name or you don't rename, then it shows as a ND. You can see now it shows the EM because I just rename it. So it's also better you try to rename it, then it show the name which you put. So we find out 0.986 to 0.988, just I apply the same. And import. And put it's a EM or emissivity. So now it's create another layer of emissivity. Okay, so we find out this type of emissivity layer. Okay. And finally, fourth step, it's called brightness temperature. Okay, compute brightness temperature. So for the brightness temperature, we are just call one image. It's called the thermal. I put the variable as thermal, and then it's come from this image. So just put the select function, select, and select the specific thermal band name. So for this case, thermal band name is STB10. Okay. Just use the STB10, and this band we need to reproject the pixel value, mainly digital number to reflectance value of thermal. So just use here the multiply function and multiply with the scale value. Yeah, this is the scale value. Where is it? Yeah, this is the scale. Just copy and also add the offset value. So now it just show the result. So now I try to add the layer of thermal band, and now run the code. Okay, so after computing the thermal band, it show this type of thing. You can also stressing that it look more better result. Just run and apply. So I put the grayscale. So we find out this type of thermal band visualization. So now after computing the thermal band, we need to apply the final equation of LST. So if you check this paper, so LST, this is the final equation of the LST. So this is the LST equal, we find out that TI represent the sensor brightness temperature. So mainly thermal band or brightness temperature, we already compute, divided by 1 plus lambda plus TI divided by mainly brightness temperature divided by rho, then multiply logarithm emissivity. Okay, so in this formula we already compute all of those. We already compute the brightness temperature, already compute the emissivity value, we already compute. But if you check this type of lambda, this type of rho, so this it's a constant value. Okay, suppose Planck's constant which is equal to this is value. Okay, one Planck's constant. Okay, you can also compute, you can see show the velocity of the light equal to, and the sigma basically Boltzmann constant value. So it's this type of constant value, but other variable, suppose brightness temperature or emissivity is already done. So now we simply use this type of constant value and finally compute the LST using this formula. So let's go try to apply this formula and then check what happened. So take a variable, suppose it's a final step, fifth step. So take a variable LST and then call the thermal band. Okay, so you can see in this case we are just only use the thermal band. Okay, so this equation or this LST equation we can only apply for the thermal band. Okay, we can only apply for the thermal band this equation, not the all of whole image, all of bands don't need. Okay, so that's the reason I simply use the multiply this value, mainly convert the digital number into reflectance value only for the thermal band. Okay, because my final LST equation is only applicable for the thermal band. So just I call the thermal band. Okay, thermal, and apply the expression and then put my equation in here. So equation when you put, so in this case TI or thermal band, so suppose I put the TB or TB. Okay, thermal bands divided by 1 plus 0.00115, so it's a constant value. Okay, and then this value multiply, so it's multiply TB brightness temperature divided by 1.438. Okay, and these things simply multiply logarithm emissivity. Basically just put here the, I put suppose EP. Okay, emissivity. So this is the equation. Just close. So just I close the equation. Okay, and this equation mainly we find out the result in Kelvin unit. Okay, basically brightness temperature Kelvin unit, but when you convert the degree Celsius, just simply put subtract 273.15, so let's convert as a degree Celsius. So in this equation, we need to define only for the variable. Suppose in this equation TB and EP is only variable, other is the constant value. So just I define, just put the comma sign and curly brackets, just now define what is the TB, what is the EP. So just I define TB, basically it's come from this thermal band, and what is the EP, EP basically this one, this EP, this EP it's come from emissivity. Okay, so you already compute the emissivity if you check EM. Okay, so now finally I just add the layer, suppose my dot add layer of LST and then check the result what happened. So you find out this type of result if you check to the white color, and it show the STB10. Okay, STB10 it show. So you can simply rename it. Suppose I put the rename dot rename and I put the name suppose LST and run the code. So now it show about the LST. We find out that, and if you check just stressing 98%. So you find out this type of temperature value, and I want to add the color suppose to display. Suppose low temperature, so this type of then use this type of green color. Then use suppose yellow color, and high temperature it show that this type of red color. Just apply. Okay, so we find out this type of temperature map. Or if you want to also check the another stressing level. Okay, so which one is more perfect, simply check. Yeah, so you can see find out this type of visualization for the stressing level 90%. Suppose check suppose 90, then it just set this type of mean and max and display the result. So you find out this type of visualization. Suppose stressing level 2 sigma, then check. So now it set this type of visualization and then set the color. So I just use it and then just import. And if you want, you can also put this opacity. You can say opacity. Suppose just I simply decrease the opacity level, so then we can easily get the base map. Okay, suppose it's optional. If you want, you can also ignore this type of part, but I will show you this process also. So now if you more stressing level, just apply, just decrease the opacity. So now it just visualize the, if you check, we find out the base map. Okay, base map, it also reflect on our map. So from where you can easily get the idea. You can check this type of place. We find out that high temperature, okay, it's a barren land or it's a water body or lake. Okay, you can see. So just opacity when you decrease, then we also find out the base map. Okay, behind the map it also visualize. And this type of place we find out the high temperature, also this type of place. Okay, and this type of place the low temperature. Okay, and if you check the value, suppose just click on the Nespero tab and then click. So now we find out that for this type of coordinate, what is the value of LST? We find out 42.15 degrees Celsius. Okay, for this type of red color. If you check suppose this type of place, we find out the result 25.87. Okay, you can see for this type of place is the low temperature due to the vegetation or others or water body. Okay, but for the urban land we find out this type of place, airport, we find out the high temperature. Or this type of barren land or build up, it absorbed the lot of sun heat absorbed. So that is when we find out the high temperature. So it also more better visualization when we add the urban heat island. Okay, we can easily identify which area is the more temperature or more warmer than the periphery region. So we find out this type of map. It's called the LST, land surface temperature. So further we can simply export this type of map and make the proper map for our research paper. Suppose in this paper if you check, it also use, just simply export this type of result as a GeoTIFF file format and further use the ArcMap or QGIS software to represent this type of, you can see range, basically LST. Okay, also make the classification. You can see 23.26, 26 to 29, 29 to 32 and greater than 32. Okay, after downloading we are just use the ArcMap or QGIS software to produce this type of map for the research paper or presentation. Okay, so this is the LST. So now from the LST we can also compute urban heat island and identify a more warmer region. Okay, so this is the formula. You can see urban heat island. Okay, urban heat island formula. You can see this is the citation about this formula. So this formula basically LST minus average LST divided by standard deviation of LST. So whenever just use this formula, we can easily get the urban heat island and identify the urban heat island map. So in this case, we need to compute the two value, mainly average value of LST and also standard deviation value of LST. So let's go try to compute. So we took R1 8 island. Okay. So this formula is LST minus average LST value divided by standard deviation LST. Okay, so just we compute this formula, then we can easily compute the urban heat island for our study area. So take a variable, suppose mean LST we just compute from our LST. So just call the LST. From this LST mesh, we just compute the average LST value. So same process, just apply the reduce region. Yes, please. Any question? Oh, sorry. Okay. Yes. Okay, so just take the LST dot reduce region function, and then compute the average LST from here. So just make a dictionary and put all of argument. First argument is the reducer. I put e dot reducer dot mean. Okay, so now it's compute the average LST. Then put here geometry. Geometry basically it's a ROI. Okay, so simply put here that your study area ROI. And then put here the scale. Scale is the resolution of satellite imagery, 30 meter. Okay, now print the result. We find out the average LST value. So just call the mean LST and run the code. So now let's check the result from console tab. We find out that one dictionary. This is the average LST. We find out that 33.05 degrees Celsius. So this is the average LST value in the Dhaka city in year of 2024. Okay, so now I need only for the value. Okay, so for that same process, just put the values function and then put the get 0. Now run the code. So now it's just extracting the value computed object, but I need the number. So simply define ee dot number, because this value further I also use another equation as a number. So just put the e dot number. So now it work as a number. Okay, we find out the computed number computing. So this is a number. Same process just apply and also put the note. Suppose it's a it's optional. Just you can put the note. Suppose average LST. So now it display the average LST in Dhaka city in year of 2024. We find out. Same process just apply and compute the standard deviation of LST in the Dhaka city. So suppose I put it's a standard deviation STD, and I put the variable name STD and function STD DEV. Okay, standard deviation. I note suppose STD standard deviation. I want to print. Just copy. So now it show the result standard deviation value in the Dhaka city 2.09 degrees Celsius. Okay, standard deviation value of Dhaka city 2.09 degrees Celsius. So now we compute this value average LST value and also compute standard deviation of LST value. So now we can easily apply the urban heat island. Okay, just use the equation and then compute the urban heat island for our study area. So for that, just take a new variable. Suppose I put the variable name is USI, and I already calculate LST. This LST subtract with average LST, mainly mean LST. Just copy this variable because it is stored the number of mean LST. and then divided with standard deviation of LST. Just copy and paste here. And if you want, you can also put the rename as a USI. So now add the layer of Arvanite Island USI and run the code. So now you find out this type of map. Let me show you. So we find out this type of white color. So default color, we find the white color. So this type of place, we find out the high temperature. And this is the urban heat island map. So urban heat island refers to a phenomena where urban or metropolitan area experience significantly higher temperature than their surrounding rural area. And this temperature is difference primarily caused by human activity or modification up to the natural environment. Okay, so this type of place we find out the higher temperature, but this type of black color is the lower temperature we find out. Okay, so you can see this type of place is the high temperature, and this type of place is the lower temperature due to the natural activity, suppose vegetation, water body we find out. But this type of place we find out the high temperature. And in the Dhaka city, if you check this type of place, we find out that urban heat island zone, because it's the more warmer than their periphery region. We find out the more warmer. Okay, and there's a lot of causes. Suppose lack of vegetation. Okay, basically this type of place we find out the lack of vegetation. Basically, urban areas have the fewer trees or green space area, or reducing the cooling from the shade of evapotranspiration. Okay, suppose I have a trees or vegetation someplace. So this type of place easily cooling by the evapotranspiration. Okay, from the cooling shade, or we also find out the evapotranspiration is high in the for vegetation area. So this type of place is the barren land, or this type of place is the concrete. So that's why there is no vegetation, there is no shading, there is no evapotranspiration activity. So that's the region we find out the more warmer or more temperature. As well as in the Dhaka city, you also find out the worst heat. Different types of vehicle or air condition or industry or other source release the heat directly into the air. Okay, that's the region. You also find out this type of place, and you can see this is the airport region. Okay, so it's a more warmer for the different types of vehicle or airplane, and its source release the heat directly into the air. And also tall buildings. Okay, we also find out that Dhaka city tall buildings and narrow streets. Okay, it's the trap the heat and increasing the local temperature also, and reducing the airflow. Suppose tall building, it also reducing the airflow. So there's a lot of region beyond the urbanite island. So you find out this type of place, this type of problem. Okay, so this is the map. If you want, you can also represent more better. Suppose you just add the color. Suppose I want to add the color, and I think it's more better just show the binary class. Suppose 0 and 1. 0 display suppose non-urbanite island area. 1 is represent suppose urbanite island area. So for that, if you want, you can also use this type of color. Suppose I just put this type of white color, this type of color as a non-urbanite island, and urbanite island, and to show this type of red color. Okay, then apply. So now it display this type of map. We find out. So you can see this type of red color indicating about that urbanite island in year of 2024. Okay. So now we can also compare the result. Suppose very first time 1990, then check what happened. Okay, so in 1990 we find out the lot of tree cover or vegetation or water body. So then we find out the very few urbanite island in 1990, and yearly and day by day it also increased. If you check, this is the result We find out the Arvanite Island. So now we find out this type of place is Arvanite Island, and how I can compute the effect of Arvanite Island. Okay, where is the high effect, where is the low effect or middle of Arvanite Island. So for that we use the another indices. It's called the urban thermal field variance index. So you can see this is the urban thermal field variance index. So it show the result. Okay, and this is the formula, LST minus average LST divided by LST. So when you compute this formula, we find out the urban thermal field variance index, and it show the result. Where is the high effect of Arvanite Island, where is the low effect of Arvanite Island. So let's go try to compute and check the value. And if you want, you can also just import the visualization parameter. Just copy. And I could say Arvanite Island. Website. So now we discuss about that another index which is called the urban thermal fields variance index. So there are a lot of uses. Suppose if you want, you can, it's identify mainly thermal comfort zone. We can easily identify using this index in the thermal comfort zone. Okay, so basically indicating the how hot or how cool each area is compared to the average temperature of the entire region. And we can apply easily this formula. This formula basically urban thermal, it's a LST minus mean LST or average LST, mean LST divided by mean LST. So this is the formula. So when you compute this formula, we can easily get the urban thermal field variance index. This index used to quantify and assess the intensity of urban heat island based on land surface temperature. And we can easily identify thermal comfort zone. And thermal comfort zone, it's indicating about that how hot or how cool each area is compared to the average temperature of the entire region. Okay, and it also help you to show the result where urban heat stress is higher. Suppose if I find out this value, suppose this value, if this value is high, it indicating about that your urban heat stress is higher. Okay, and also identify hot spot. Okay, identify hot spot in the cities. Okay, which place is more hot or hot spot. So you can also identify using this. So in this case, I already compute all of those. Mean LST already done. So just I apply this formula. So urban thermal field variance index. And call the LST. This LST simply subtract. So put here the subtract with mean LST. Then divided with mean LST. So now map.add layer and call the urban thermal field variance index and run the code. So now it show this time. Let's zoom. So it show this type of thing. Just let me stress and then check the result. just apply, or I keep suppose 3 sigma. So now this type of black color indicating about the low values of urban thermal fields index. Okay, and this type of place is the high. So in the Dhaka city, almost all place we experience the urban heat island effect. Okay, in the every place. Okay, without you can see this type of water body, and we can also make the some classification. Suppose based on the urban heat island value. Suppose if the value less than 0.000, okay, mainly negative value, it's indicating about that your excellent, okay, thermal stress level is excellent, and environment quality very good. Okay, so it's one kind of classification, very good. Suppose some place we find out the negative pixel of urban thermal field variance index less than 0. It means that this type of place thermal stress level excellent and environmental quality is very good. Okay. Suppose some place we find out the value 0. Suppose 000, then suppose 0.005. It means that thermal state is good. So you can also check some paper regarding this type of classification also good, and environmental quality good. Okay, not very good. So if this value 0.002, 0.005, it's a good, and it's a very good. Okay. Then another suppose same 0.005 to 0.010. It's a normal condition. It's called the normal. Thermal stress level is the normal, and moderate environment, moderate. It's called the moderate environment. Okay. Then suppose another, or if you can simply search, suppose let me show you the value also. Urban thermal field variance index, simply search various index range, simply put the range, search on the Google. And you can check this type of image. Okay, suppose you can see, also check this type of paper also. So you can see we find out this type of things. If the value is the negative, mainly there is no effect of urban island. Okay, if the value is the less than 0, okay, less than 0, it means that there is no effect of urban island, excellent. Okay, or thermal stress level are even, you can see when it's increase the value, and if the value 0.020 greater than 0.020, it's strongest. Okay, and very bad situation. Okay, when you find the very poor, or we find out the very bad situation, or severe heat stress, we find out if the value greater than 0.020, this type of things. So this called the thermal comfort level. Okay, thermal comfort level. So if the value is the less than 0, mainly negative value, it's very excellent thermal stress level, and environment quality is very good. Then second step, if the value 0 to 0.005, it's a good. So now we create some classification and identify some of the hottest spot. So from this type of range, it indicating about that if the value is greater than 0.020 or greater than 0.015, it's identify about the hottest spot. Okay. So now how I can identify? So this is my map. Okay, so from this map, suppose I want to identify only for the very good environment or very good excellent thermal stress level. So how I can identify, or I want to identify suppose good only for this type of range I want to identify, or I want to identify suppose moderate environment, this type of range. So how I can do it? So it's called the classification problem. So let me show you the one example, then it will be more better, you can get the idea. Just simply paste this visualization. I put the name, suppose it's a UTFBI. And if you check the level, suppose just click on the inspector tab. Suppose I just click this type of place to display the result for urban thermal field variance index. We find out the negative value. Okay, this is the negative value. Okay, it shows the negative value. And it show the LST because we are not use the rename function. So when you put the dot rename, then it also rename and show the urban thermal variance index. So now we find out the negative. So you can see this type of place at the excellent temperature because it's a negative. But when you work with this type of place, let's check 0.2. So it's a very high. So environment quality is very bad for this type of place. So now how I can identify? So it's very easy. Just use the range. Suppose take a variable. Suppose I put the variable name is that excellent area. So now just call the urban thermal variance. Okay. Apply a, suppose put the less than 0 point or 0. So now display. So map.add layer. Oh, sorry. Map.add layer and call the excellent area. Okay. And run the code. So now this variable is stored only for this area. Which area we find out the less than 0, mainly very excellent or good quality. Okay, so you can see it show the binary class. Okay, we find out, and if you want, you can also add the, suppose it show the two color. You can see, I think this type of white color is the good quality. Okay, or comfort zone. This type of white color, I think it was a better. We try to apply self marks and make only for the single class. So self marks, and then add the color. Suppose I put the color single color. This type of excellent area I want to display as a green color. Okay, so green color indicating about that excellent area or very good environment, not much high temperature. And this type of place, it means that this type of place is not high effect of urban heat island or very good environment. Okay, so we find out, you can see this type of place, we find out that it's not much higher, okay, in temperature. So if you check, so we'll just click on here and then check the value of urban heat island. What is the value? Find out negative. Okay, negative. Suppose let me check from here. And this type of place we find out that suppose flow of air. Okay, suppose this type of place is not have the high building. Okay, so that the air is easily flowing or near to the river or near to the lake or vegetation area. Okay, so that's the reason we find out it show the negative pixel. So we find out this type of place is the not much effect of urban heat island. So now I want to identify suppose very bad area or very poor environmental quality. So this type of place is very good environmental quality. Okay, so now we want to identify suppose very bad area or severe heat stress area. Okay, high heat stress area. So just take a variable or hot spot area. There was hot spots area. Same process I apply. Suppose just call the, just use the same line of code. And in this case I simply took the worst area. I put here greater than, suppose 0.020, and I want to identify hotspot area. Just add the new layer for hotspot area. Just call the hotspot area this variable and add the color, suppose red. So red, and run the code. Right. I'm going to add the layer name. Suppose it's a very good environment, man, and we put here say forced or very poor environment or hotspot area. Okay, high effect of urbanite island. So now run the code. So now we can easily identify very good environment area and also very poor environment area in Dhaka city. So I can see. So now this type of red color indicating about the very bad environment area, because they are high effect of urbanite island, this type of red color. Okay, we find out that this type of place, we find out the very high effect of urbanite island or very worst area. Okay, because the severe or hotspot area, so this type of place is more temperature. Suppose there is no trees, there is no, there is very high building. Okay, and this type of place, suppose we find out that lot of vehicle or aeroplane release the heat. Okay, but this type of place only find out the barren land. Suppose some place is the near to the vegetation or near to the river or lake, so this type of place we find out the low urbanite effect. Okay, so this is the process we can apply this type of value, and then we can easily create the hotspot area or good, or can also consider the environmental quality also based on urbanite island or based on thermal stress level. So this is a way you can also read some paper regarding this type of topic, then you can get the more better idea how it will work. Okay, anyone any question, you can ask me please. Any question? Okay, I think there is no question. I'll try to practice. So now we talk about that how we can easily make the time series chart. Okay, time series chart of LST. Okay. So now we talk about the time series analysis.